Okay, let's just dive right into this explainer, shall we? Today, we are looking at how some incredibly high-level math, stuff straight out of international academic conferences, is actively reshaping our highest-stakes industries. You might think of advanced mathematics as something that just stays locked away on university whiteboards, right? But what we're looking at today is a fundamental shift in how computers calculate reality itself. And I literally mean reality. Everything from how airplanes fly to how your smartphone streams data. We are talking about a massive, rapidly growing field known as probabilistic numerics.
So what does this all actually mean? Well, the absolutely crucial point here is that instead of just spitting out a single, rigid number, these probabilistic solvers give you an answer, but they also tell you exactly how confident they are about it. They basically treat computation as a form of Bayesian inference. To put that into perspective, imagine asking your GPS how long a drive will take. Standard math says 30 minutes. But this is like the GPS saying, hey, I'm 95% confident it'll take 30 minutes, but there's a 5% chance of a massive traffic jam that's going to make it 45. Having that extra context completely changes how you make decisions, right?
So here's the roadmap for today. First, we'll meet the probabilistic solver. Then, we'll hit aerospace and mechanical engineering, move on to chemistry and deep space, tackle telecommunications and cloud computing, and finally, we'll wrap up with the future of uncertainty. Let's get to it.
Section 1. Meet the probabilistic solver, a paradigm shift in computation.
Now, standard numerical methods, they give you one absolute answer and just completely ignore model uncertainty. It's literally like a weather forecast that just confidently says it's sunny, completely blinding you to anything else. They leave you with this huge blind spot. But probabilistic numerical methods, they actively track that uncertainty. It's like saying, okay, 95% chance of sun, but hey, 5% chance of turbulence. This is exactly what was explored in a super foundational 2025 conference paper by Yao, Tronarp, and Bosch on propagating model uncertainty through these solvers. We're talking about moving away from blind trust in a machine's output over to calculated confidence. Because when lives or, millions of dollars are on the line, you don't just want an answer, you need to know the machine's exact margin of error.
And to really ground us in the source material, just look at how ridiculously fast this field has evolved. There are barely 12 months separating the first international conference on probabilistic numerics in France in 2025 and the second one in Finland in 2026. The sheer volume of diverse, industry-ready research that exploded onto the scene in just those 12 months is honestly staggering. It proves for sure that this isn't just some abstract theory anymore. It is a rapidly adopted technological framework.
So that brings us to a really important question. How do we bridge the gap between all this abstract academic theory and actual physical safety? Like, how does knowing the mathematical uncertainty of a calculation literally keep a physical airplane safely up in the sky?
Section 2. Aerospace and Mechanical Engineering, Grounding Math in Reality. Well, we've got actual 2026 conference papers directly applying these solvers to incredibly real-world dangers. Over in aerospace, you have Capmes Pernay and their colleagues using these models to reconstruct wind turbulence using LiDAR sensors, all while an aircraft is literally in motion. Think about that for a second. The plane's computer has to process all this incredibly messy data instantly to adjust for turbulence. By using probabilistic methods, the system understands exactly what it doesn't know about the wind, which allows for much safer, smoother corrections. And then, over in mechanical engineering, a paper by Rogers, O'Connell, and Champneys applies this to statistical finite elements for vibration problems. This is literally about making sure things like bridges, engines, and massive structures don't just shake themselves apart, all by modeling the uncertainty in how materials actually vibrate in the real world.
Now, underneath all of those crazy engineering feats is some incredibly dense math. We're talking ordinary and partial differential equations and Hamiltonian dynamics. But look, you don't need to be a calculus genius to appreciate what's happening here. The key takeaway is that these are the exact equations that govern motion, heat, and energy in our physical world. Papers presented at these conferences by researchers like Toyota, Wayland, and DeSuster show us that probabilistic solvers are perfectly suited to tackle these massive, complex equations. They are basically weaving a safety net of probability into the very mathematical laws of nature. It's absolutely brilliant. And all this momentum naturally pushes us to ask an even grander question, right? If this works so well for airplanes and giant engines, what happens when we scale this math all the way down to microscopic gas reactions, or scale it all the way up to the size of the entire universe?
Section 3. Chemistry and Deep Space, from Micro to Macro.
Okay, let's look at the micro level first. We have a 2026 paper by Miller, Zhao, and Peterson that models gas phase reaction kinetics. In chemistry, molecules are constantly colliding and reacting in ways that are just inherently random and unpredictable. Probabilistic numerics steps in to help chemists model these totally chaotic, invisible reactions, giving them a crystal clear understanding of the margin of error. But then, zoom all the way out to the macro level. We're talking about a 2025 paper focusing on deep space. Entire industries and academic fields are out there modeling everything from microscopic gas to literal astrophysics by treating the unknown as a quantifiable probability.
Actually, let's linger on that deep space concept for just a second, because it is absolutely fascinating. Researchers at the 2025 conference, specifically de Soester, Colmont, and Lee, proved that you can actually solve Einstein's equations of general relativity as a problem of Bayesian inference. No way, right? They took the absolute most foundational laws of physics, the equations that dictate how gravity bends space and time itself, and proved that even these calculations benefit massively from reasoning about computational uncertainty. It's a profound, game-changing shift in how science interacts with the universe.
But hey, enough about space and molecules for a minute. Let's leave the physical sciences behind and bring things a little closer to home. How does this impact the digital infrastructure we rely on literally every single second of the day? Like, how do we handle computational uncertainty when data is constantly bouncing back and forth between edge devices, like the phone in your pocket, and the massive cloud?
Section 4. Telecommunications and Cloud Computing, the Digital Realm.
Well, a really remarkable 2025 paper by Hu and colleagues brilliantly illustrates how probabilistic solvers are actively optimizing the internet as we know it. Just think about your smart devices for a second. They have pretty limited processing power compared to those massive cloud servers, right? Well, this research allows a device to calculate its own uncertainty in real time. If your device is highly confident it can process a task accurately, it just does it locally to save time and bandwidth. But if its mathematical uncertainty crosses a specific threshold, it intelligently offloads that computation straight to the cloud. The software is literally judging its own capability on the fly, based entirely on its level of certainty. That is absolutely huge for telecom and cloud computing.
Section 5. The Future of Uncertainty. Embracing the Unknown. And all of this creates a very clear industrial mandate. We simply have to stop demanding a single blind answer from our software. We need to start quantifying computational confidence, and we need to treat all complex computation as a form of inference. For industries to survive and innovate in the future, whether they're building better jet engines, predicting chemical reactions, exploring the cosmos, or just managing global internet traffic, they have to stop ignoring model uncertainty. The era of just blindly trusting a standard computer output, yeah, that's ending. We've got to start demanding software that fundamentally knows its own limits.
So, I'm going to leave you with this provocative thought to chew on as we wrap up this explainer. I want you to imagine a world where every single piece of software, from the anti-lock brakes in your car to the massive servers running the global stock market, doesn't just calculate, but actively reasons about its own accuracy before it takes action. Could mathematically embracing what we don't know actually be the ultimate key to unlocking the absolute highest level of industrial precision humanity has ever achieved? Thank you so much for exploring this fascinating shift with me today. Keep asking those big questions and always keep demanding to know the probability behind the answers.